Hello, it is Danica.
And Jordan.
And we are here to talk about our homework 11 for our 460 Monte Carlo course. So the problem prompt for today's homework is that we need to use inversion of the cumulative distribution function to develop methods for sampling variates from each of the following probability density functions. And he wanted us to do parts A through D and then part G. So we are going to go into those. For part A, so the function is 1 over 20 on support from 5 to 25, and that is a uniform distribution. So this is our MATLAB code we put into MATLAB. Our lambda is 1 over 5, so doing a little bit of conversion there, but the rest of the code is pretty straightforward. And then these were our results. So f obviously is x over 20, and then our graph is relatively uniform. And then Jordan's going to do part B for us really quick.
So part B is a special type of distribution. It's not really a uniform, but it does, if you were to go from 2 to 6, take the integral of it, it equals 1. So it is a distribution going into this. We did the solve function, and the f underscore gives a kind of a crazy explanation that's way too long. That doesn't seem like it looks right to me. So what I did is we looked at Wolfram alpha, and we plugged it in and did some functions there. We found that 4 times the square root of the random number plus 2 is actually a function that can generate the random variate. It seems like MATLAB's kind of lacking in some of these areas sometimes whenever you're doing this, so we had to rely on Wolfram alpha for a few of these problems. But it does generate from 2 to 6, and it does have an area of 1. Moving on.
Moving on to part C. So this one is an exponential distribution going from 0 to positive infinity. Once again, here is our MATLAB code that you can see, and then our results look to be exactly what we would expect. It is an exponential curve, and when you look at the graph, it looks like the mean is about 5.
So moving on to this next one, this is a double exponential. So this one was actually kind of hard to kind of generalize, because we have to generate not only the regular exponential on one half, but generate the other exponential on the other side, which is negative exponential. To do this, we had to use Wolfram again. It seemed like there were some errors whenever we were trying to use stuff. So it's relatively close to what the solve function did in MATLAB, but we just had to tweak it a little bit. And the big thing that is, if r, the random variate, is generated and it's underneath of 0.5, we do one function, which is one side of the exponential, and if it's greater than 0.5, we generate the other side of the function. So here we can see its mean is at 0, and it has exponential going both ways. Moving on to the final one, part G. This one was kind of awkward. We had to generate with 2 for loops, the one side of the triangle and the next side of the triangle. It was kind of weird in MATLAB 2 doing this again. We had to do a if the random generated variate is less than a, it will generate that triangular distribution. This one we can change the a value to be anything from 0 to 1, and we'll create a triangular distribution. We chose to show you 2, but you can be like for anything from 0.5 to 0.7. And with that,
that is all. Thanks for watching, guys.